Okay, back for part two, later on in the afternoon for me, but probably just a moment or two later for you. Uh, so we're just coming off of looking at the standard model and some of the basic things that we have information about them. I want to dig into quarks a little bit more. So historically, quarks were a theory proposed independently by two different scientists, Murray Gell-Mann and George Zweig, in the 60s as a way of explaining all of those additional particles that were being observed. Essentially, as this map got bigger and bigger very rapidly in the 60s, there was a desire to find some way to explain where so many particles were coming from, as instead of them being all separate different things like the proton and the neutron. And so the concept of quarks was what they came up with. An important thing to know about quarks is that quarks in this theory are never observed in isolation. So no one has ever observed a up quark or a down quark, even though these make up all of the protons and neutrons that we have inside of the nucleus. There, as far as we know, charge only exists quantized in units of 1 electron. But for example, using this theory to describe a proton as being built up from 2 up quarks and 1 down quark, with a positive charge of 2 times 2/3 plus a negative charge of 1/3, helps to explain how protons and neutrons transmutate when beta decay happens. There is strong evidence that quarks actually exist and are not just a theory to explain what's happening with the wider variety of particles from collision experiments, from electron-positron collision experiments. As I mentioned, I think on the last slide, up and down quarks make up the vast amount of matter that we observe because of the different masses and the different energies. The higher energy quarks tend to decay very, very quickly into less energetic particles. I mentioned also that antiquarks exist. So for U, D, C, S, T, and B, the antiquarks are noted with a bar across the top. So U bar, D bar, C bar, S bar, those are the anti-charm, anti-strange, anti-up, and anti-down quarks, which is how you read them. And so how does this theory work? The theory works by saying that hadrons, which are all of the normal matter that we see that are not leptons, are composite particles, meaning they are built up from quarks. And there are two different ways that hadrons can that hadrons can be built up. They can be built from 3 quarks joined together, in which case these are baryons. And you can also have, say, 3 antiquarks combined to make antibaryons. An example of this would be the proton is a combination of up, up, down. As I mentioned before, it has a charge of +1, and it has a spin of 1/2. But the antiproton would be anti-up, anti-up, anti-down, and so it would have a charge of -1, still a spin of 1/2. The neutron is the other common baryon, up, down, down. In this case, the +2/3 from the up and the -1/3 from the 2 downs combine to give 0 charge. But there are many others. You can use any quarks together to imagine up a new particle, and you can then look to see if you ever observe a particle with those particular properties. The one that is the most helpful for distinguishing would be the mass, or the spin, or the charge. The other type of hadron is the meson. Mesons are built from one quark and one antiquark. And so these would be examples like the pion, an up and an anti-down. This has a positive 1 charge because the up quark has a plus 2/3 charge, and the anti-down also has a positive charge, positive 1/3. So 2/3 and 1/3 give you a charge of plus 1. There's another way that a pion can be built. The pion 0 is a combination of an up anti-up and a down anti-down. And so it has a charge of 0. And there are more here. And these are not comprehensive. You can go to websites to find all the many different baryons that have been observed in all the possible combinations here. And then some of which have been predicted, but obviously not yet observed. Note that when you look at quarks being built from quarks building up to form a baryon, the charge adds, but the masses do not. So here, this has a mass of 0.938 giga electron volts. If we look at 2 ups and a down, 2 ups and a down would add up to like 2.2 mega electron volts times 2, 4.4 plus 4.7. So that's only about about 9 MeV. And the proton is about 900 MeV. So there's a different aspect there that bestows mass on baryons. So you don't add up the masses to find out what the mass of the object is. The other thing you may notice is that it's a little strange that the spins add here to form a spin of 1/2. But here, the spins are adding to give a 3/2. Spin is a vector, and as such, you can create different particles in different ways with different spins, depending on whether those vectors are all oriented in the same direction or if they are oriented against each other. In this case, the up quarks have their spins oriented in the opposite direction, so only the down quark is contributing to the spin. And there are different particles that actually have the same quark makeup, but different orientations for the spin, so they are different particles. An example is the delta 0 particle and the neutron are both built from an up and 2 down quarks, but the neutron has a spin of 1/2 and the delta 0 has a spin of 3/2. Mass is really tricky, so we're not even going to mention that one. With all of these different possible combinations, you might be wondering, could you just build anything? And more importantly, could anything just turn into anything else? We know that in beta decay, neutrons can turn into protons. Could you have anything turn into anything else? Well, it turns out that obviously, no, you can't. All of our conservation laws need to be followed. And one of the most important ones is the conservation of energy. So the conservation of energy means that high mass particles like the delta 0 can break down into lower mass particles like the proton and the pion. But it is much less common for small mass particles like the pion and the neutron to turn into K plus and sigma minus. The neutron and the pion would need to collide with an extraordinarily large amount of energy for there to be enough energy to produce these larger masses. And in fact, this is what things like the Large Hadron Collider are for, is for having hadrons collide to have these very high energy collisions that allow for the production of these high mass baryons and high mass mesons. In addition to making sure that energy is conserved, Decays must also preserve the baryon number, which is 1/3 of the number of quarks, and the electric charge. Some people like to count the baryon number, some people like to count the quarks. We can kind of do both. Let's look at one example here, and then I'll let you practice a few. So with the delta zero, oops, I meant for this to have something covering it. There we go. With the delta zero is an up, down, down. So it is a baryon. The proton is up, up, down. So it's also a baryon. And the pi minus, the pion, is an anti-up and a down quark. The baryon number of the delta zero is 1. The baryon number of the proton is 1. And because the pion is a meson, its baryon number is 0. So in this case, the baryon number is 1 on both sides. If you'd like to look at it in terms of the quarks, you can do that by counting the quarks and subtracting any antiquarks. So in this case, the delta zero has 3 quarks. The proton has 3 quarks. And the pion has 1 quark and 1 antiquark, so it has 0 quarks. So 3 quarks on the left, 3 quarks on the right. Note that at no point in time do we care about what types of quarks we have. Quarks are allowed to change into other types of quarks. So the fact that here we have an up, down, down, and in the proton we have an up, up, down, and there's also an up, an anti-up, and a down here, doesn't really matter. It's not like the downs are splitting up or something. Right? What we have is just a conservation of the baryon number. The other thing that is conserved is charge. Oops, go back. So in this case, the delta zero with its up, down, down has a charge of plus 2/3, minus 1/3, minus 1/3. So this is neutral, hence the 0. The proton we know is plus 1 from the 2/3, 2/3, minus 1/3. And the pi minus is an anti-up is negative 2/3 and a down is minus 1/3. So we have negative 1. 0 charge on the left, 0 charge total on the right, so charge is conserved. It is possible for this reaction to take place, assuming that there's enough energy in the delta zero to produce the mass of the proton and the pion. Using this table here, you can go ahead and check to make sure that all of these other reactions are possible if enough energy exists. So you might want to pause for a minute, try to do some of those, and then I'll show the answers. You're going to want to pause, 5, 4, 3, 2, 1. And now you've done your work and you wanted to check your answers. Here are the answers. I'll move my face out of the way for a moment. I'm not going to stay here for too long, but you can go ahead and pause and check your answers. I've mentioned here something about strangeness because you'll see strange and anti-strange quarks involved here. More about that in just a moment. 3, 2, 1, and we'll keep going. Another quantity that's defined for the generation 2 and 3 quarks specifically are properties that are appropriately called charmness, strangeness, topness, and bottomness that is conserved in some decays, but not all decays. In cases where the strong force is involved, the decays will conserve the amount of charm, the amount of strange, and the amount of top and bottom. But if the weak force is involved, those numbers can change. In the IB syllabus, we really only focus on strangeness. So you'll only see S quarks involved and count those as opposed to charm, top, and bottom. Strange quarks have a strangeness of -1, and anti-strange quarks has a strangeness of +1. No other quarks have strangeness. I'm now just realizing that I think I forgot that the strangeness of a quark was -1 and an antiquark was +1. And so probably all the answers on the previous sheet were backwards with those values. Yep, that's what it looks like to me. So my mistake there. Strangeness is conserved when the strong force is involved, but can change with weak force interactions. Weak force interactions are slower. In this case, the delta zero decaying to the proton and the pion. As I noted in the previous slide, the strangeness is changing. Oops, I got to pause for a second. I got to check something. Found it. Okay, the delta zero was the first reaction we looked at. We didn't check the strangeness, but let's do that quickly. So here, the delta zero, up, down, down. The proton, up, up, down, and the pion, anti-up, down. The strangeness of both the delta zero, the proton, and the pion are all 0. In this case, strangeness is conserved. In that reaction, the strong force is responsible for the decay, and so it will be quite quick. The lambda zero particle, on the other hand, the strangeness changes. The strangeness of the lambda zero particle is -1, but the strangeness of the proton and the pion are both 0. And so in this case, the strangeness is changing, and so the weak force is responsible for that decay. And as its name implies, the weak force will cause that decay more slowly than the strong force. Problem solving in here is very much limited to confirming that a decay is possible or describing the properties of a particular lepton or, a particular hadron, like a particular baryon or a particular meson. And so these questions might look like, what are the properties of up, down, top? And so that would have a charge that would be +2/3 from the up, -1/3 from the down, and +2/3 from the top. So it would have the same charge as a proton, +1. It would have a baryon number that is equal to 1 because it has 3 quarks, so it's a baryon. Its strangeness would be 0, and its antiparticle would be anti-up, anti-down, anti-top. Its properties would have a charge of -1, a baryon number of 1, and a -1, and I got to check that. A strangeness of 0, and its antiparticle would be up, down, top. So we'll have to check later on the baryon number there. If we were looking at charm, anti-charm, the charge would be 0. Any particle and its antiparticle will cancel out charge. Its baryon number would be 0 because it has only 2 quarks, so it's a meson, not a baryon. Its strangeness is 0, and it is its own antiparticle because if you do the anti-charm and the charm, it's the same particle. Other types of problems are looking at whether a certain decay is possible. Could it decay, and then is it weak or strong force mediated? And if it can't, what's the reason that it can't? So for example, here we have the pi minus and the proton turning into a pi minus and a sigma plus. We know what the pi minus is. That's an anti-up down, and the proton is up, up, down. But what's a sigma plus? I need to go back and look again. Sigma plus, oh dear. I didn't have it written down. Let me pause for a second. Okay, found it. It is an up, up strange, which kind of makes sense because it's +1, so it needs an up. It needs 2 ups and a down version. That's what the strange is. Since it has a strange quark, it has a strangeness of -1. Nothing else has a strange quark. In this case, charge is conserved, baryon number is conserved, strangeness is not conserved, so this decay is possible, and it would be mediated by the weak force. Neutron plus a proton leads to a proton and a pi zero. In this case, charge is conserved, +1 and +1. Baryon number, though, is not conserved. This has a baryon number of 2, and this, because the pion is a meson, would have a baryon number of 0. So we have a baryon number of 2 and a baryon number of 1 on the right, so this decay cannot occur. This brings us to the leptons. So fortunately for problem solving, the leptons don't combine. They're observed independently, unless, of course, you go to atoms where the electrons are part of, say, an atom, which has neutrons and protons in the nucleus. So these exist also in each generation of matter. The electron and the electron neutrino are the most common ones. But we have the muon neutrino, the tau, and the tau neutrino. And of course, we also have the antileptons. So we have the E plus, which is the positron, the positive muon, and the positive tauon. And the antiquarks are shown with a bar over them. These neutrinos are very, very low mass relative to everything else, although the muon neutrino and the tauon neutrino are only relatively massless to their generation. Leptons always interact by the weak nuclear interaction, but not by the strong. There is a family number for the electron lepton family, the muon lepton family, and the tauon lepton family, and that is conserved in all interactions. You might remember from before that beta decay involved a electron being produced and an anti-electron neutrino. The reason for that is when a neutron turns into a proton, there are no leptons to begin with. And so if you produced an electron and an electron neutrino, it would be a family number of 2 for the lepton electrons. But if you have an electron and an anti-electron neutrino, the lepton family number remains 0. So when we have decays, we must also preserve charge and lepton family number. The energy to account for the mass needs to be obviously conserved, but leptons are quite light compared to quarks, and so we can have and observe certain decays like, in this case, the gamma here represents a photon, in this case, a high energy gamma photon that has been produced from a nuclear decay, like in topic 12, can produce an electron and a positron. The charge remains 0, and the lepton family number is 0 because the electron and the proton have lepton family number of +1 and -1 respectively. A neutron turning into a proton, an electron, and an anti-electron neutrino, we just talked about, that's beta decay. Notice here that the baryon number is conserved. Charge is conserved. 0 turns into +1 and -1. The neutrinos are neutral. And the lepton family number is conserved because the -1 and the +1 cancel out. See if you can explain this one. The mu plus here, turning into a positron, an electron neutrino, and an anti-muon neutrino. In this case, the mu plus has a lepton number of -1. It is the antiparticle. The positron has an electron family number of -1. It's the antiparticle. The neutrino, the electron neutrino, is electron-lepton family number 1, as it's the particle, so these cancel. And the anti-muon neutrino is also the antiparticle, so muon lepton family number of -1. So -1 on the left for the muon family number, -1 on the right, that's good. Electron lepton family number of 0 on the left and the right, that's also good. You might have noticed that I was mentioning the weak force, and the weak force and the strong force are mediated by particles in this model, as is the electromagnetic force. So these are the exchange bosons that are responsible for forces: the gluon, the photon, the Z boson, and the W boson. Gluons are responsible for the strong force, and there are 8 varieties of gluons. All of them have a charge of 0 and a spin of 0. And a mass of 0 and a spin of +1. The photon is responsible for the electromagnetic force, which isn't surprising because we know that we could think of a photon as an electromagnetic wave. The Z and W bosons are responsible for the weak interaction. They do have mass, and the W boson can have a positive or a negative charge. So there's a W plus and a W minus. There is a prediction that there would be a gravitron that is responsible for the gravitational force, but it has not been observed. The Higgs particle, which you may have heard was recently discovered, bestows mass on matter and was required by symmetry in the theory. But understanding what that means is something that's even beyond me completely. You'll notice here in the background, there looks like there's these little shapes here. I just want to highlight on our chart what's going on here. So in our original chart, the small shapes here are showing which forces interact with which particles. Quarks interact via gluons. And because they have charge, quarks can interact by photons. Additionally, quarks can interact by the weak force, which is necessary for strangeness or charmness or topness or bottomness to change. So all of the vector bosons, all of the force-carrying bosons can interact with quarks. The electron, muon, and tau particles are shown interacting with the photon, which is necessary because they have charge and they can interact with the electromagnetic force. They do not interact with gluons, but do interact with the weak force. Neutrinos, which have no charge, interact only with the W and Z bosons. In order to model forces that involve exchange, we have a drawing that's known as a Feynman diagram to help show what's taking place. This model here is our first example that shows electrons pushing apart from each other, which we previously understood as the Coulomb force between two negatively charged particles. In this case, the force that causes these to change their trajectories exists because there is a photon exchanged between the particles. To read a Feynman diagram, you find an arrow that represents time. Most Feynman diagrams will see drawn left to right, although some people draw them bottom to top. The vertical axis is only drawn to separate things by position. It doesn't have a physical meaning. So the way we would read this is by reading from left to right, and we observe that electrons exist for a period of time. At some moment, a photon is emitted from one electron, and at some moment later, that photon is absorbed by the other electron. By sending a photon that carries momentum away from it, the electron's path is changed. By absorbing a photon that carries momentum towards it, the electron's particle is changed. So the paths of these particles shifts with time because of the exchange of this photon. The key to understanding these exchange diagrams are vertices. Vertices are the place where three lines connect together, and they're constrained by conservation laws that show different physical processes. Here are the different electromagnetic interactions with electrons and positrons. There's one that's missing, but we can interpret this as an electron absorbing a photon and changing its path, a positron absorbing a photon and changing its path. Note that the path for a positron, which is moving from left to right, includes an arrow that points from right to left. In Feynman diagrams, arrows that point in the opposite of the direction of time are antiparticles. So this is the anti-electron. We can have an electron emitting a photon. We have an electron, then we have an electron and a photon. We have what's known as electron-positron pair production, where a photon produces an electron and a positron. And then we have pair annihilation, which is when an electron and a positron join together to form a photon. In all of these cases, the total charge remains the same. In all of these cases, the energy is going to have to remain the same, and the lepton family number has to stay the same. Note that these are all rotations of one another, and you can probably figure out what the missing one is. In order to build interactions, you can match up one with another. In this case, this vertex showing pair annihilation is joined together with pair production, the photon being the particle that links those two together. So we have this vertex and this vertex joined together to show pair production and pair annihilation. In this case, we have what's known as photon scattering. An electron changes its path momentarily when it absorbs and then later emits a photon. There are tools that exist to draw Feynman diagrams, and you should feel free to take a crack at making a few, probably starting with just the vertex involving photons and electrons and positrons. Before we go on to the next one where we look at the W and Z bosons, I want to jump back to topic 12 where there's a little piece that we didn't look at. Pair production involves the creation of a positron and an electron at the same time. The vertex shows that energy must be conserved, that lepton number must be conserved, in this case the electron and the positron, and that charge must be conserved. Again, we're fine. And we can conserve energy, like I said, if we have a photon energy that is larger than 2 times the mass of an electron times c squared, Newton or Einstein's energy mass equivalency. The energy of the photon creates more energy than is needed for those particles. But this can only work if momentum is conserved as well. And that requires that there must be a nucleus nearby. So actually, that pair production model that we made before couldn't actually work because momentum can't be conserved. This is just a factoid to know for your topic 12 pair production. The energy piece is the one that you may have to do a calculation with. For example, you might be asked if a photon of a particular frequency has enough energy to produce the electron and the positron. Similarly, pair annihilation can occur when a particle meets its antiparticle. We drew that as involving one photon, but actually it can't conserve momentum. A single vertex, the electron and positron have momentum, but a single photon is insufficient to conserve both quantities. So in fact, matter-antimatter annihilation must produce two photons in order to conserve both momentum and energy. What is the wavelength that you would have for each photon if the electron and the positron meet with a velocity of 10 to the 5th meters per second? And you can do that calculation by looking at the total amount of energy that is released from the kinetic energy and from the mass energy of these two. The last interactions that we will look at are those involving the W and Z bosons. The W and Z bosons are drawn as dotted lines. These allow us to incorporate the weak force, which interacts with all quarks and leptons. And so in these vertices, F1 and F2 are any particle. This could be an electron and an electron, or it could be an up quark and a strange quark, because the W and Z bosons interact with everything. One thing to note is that the W boson can be either positive or negative, but the Z is neutral. That means that there are certain vertices that you can have with your Z boson, but the W boson allows you to change the charge as well. We do need to preserve the quark number and lepton family number. And these, of course, can be rotated as well. The most common example that we look at here would be beta minus decay or beta plus decay. In this case, a neutron is shown as 2 down and 1 up quarks. This exists through time, but we introduce a vertex here with a W minus boson. In order to conserve charge and quark number, the down quark must turn into an up quark, or a charm quark, or a top quark, but in all likelihood, it's going to be the lightest up. The negative 1/3 charge turns into a positive 2/3 charge, but conserving charge is okay because the W minus boson carries away that negative charge. Later, the W minus boson will decay into an electron and an anti-electron neutrino. The charge is conserved in here, as is the lepton family number. Remembering that beta plus decay is the emission of a positron and an electron neutrino, can you construct the diagram for beta plus decay? In the end, we can update now our big concept of there being 4 fundamental forces. In the models that we've talked about through the rest of the 2 years, we've talked about the electromagnetic and gravitational forces as an interaction between particles with charge or with mass that's mediated by a field. However, in order to incorporate the weak and strong force, we need to move to our particle model, where the electromagnetic force is moderated by photon exchange. The weak force involves plus minus W bosons and the Z boson. Gluons are responsible for the interactions with quarks, and gravitons are responsible for the gravitational force. This also allows us to bring up some of the relative strengths of these. The strong force, if it is given a relative strength of 1 as the strongest, the electromagnetic force is the next strongest, about 1/137th. The weak force is even weaker than that, 10 to the minus 6, so about 1,000,000 times weaker than the strong force. And the gravitational force is at least 10 to the minus 41 times weaker than the strong force. This very, very low value is part of the reason why it's been difficult for people to sort out how to incorporate and how to detect gravitons. The other thing to know about the weak and the strong force is because of the nature of these particles, they don't have a range that is effectively infinite like the electromagnetic and gravitational force. They're limited to about 10 to the minus 18 or 10 to the minus 15 meters, meaning that they become so strong outside of the nucleus that new particles will be created. And in terms of the 10 to the minus 18, it essentially means that these have to be exist only inside of nuclei. And so those are the big ideas from topic 7.3. I'm sure you'll have some questions after you work on some tests yourselves. We'll deal with this next class. Thanks so much for following along.